Good afternoon, everyone. Give a few minutes for everybody to join, and then we'll get started. Okay, it looks like we've got quite a few people that have now joined. So we'll get started here. This is Permanganate 101. Just a few housekeeping items before we get started here. We are recording this webinar and everyone is kept in listen-only mode. If you have questions, we encourage you to submit those through the presentation using the question pane and GoToWebinar over on the right. We will receive a report with the question and your contact information to follow up directly with you after the webinar. If we have time at the end of the presentation, if we don't go too long, this is scheduled for 1 hour, we will answer some of those questions during the webinar at the end. If you are interested and you would like a PDF of the slides or a recording link to the presentation, please contact us. We encourage you to share the recording within your network. The contact information will be there that you see on the screen and also on the last slide, or where you've gotten the emails from for this webinar. You can also sign up there too as well, or send us information. If you'd like to register for any of our upcoming webinars, you can visit our Carus website at carusllc.com, and you'll see a webinar link across the top, and you can sign up for ones coming up in the future. We will be having a focused remediation webinar here in December, and then beginning in the new year, they're not up yet, but we will have a safety and handling of permanganate in January and a safety and handling of phosphates in February. So I'm going to be your host and one of your speakers. So I'll introduce myself. I've worked at Carus for 26 years, with the last 23 years in the technical service group. I conduct laboratory testing, product demonstrations for Carus's municipal, industrial, and environmental customers and prospective new customers. Product demonstrations can include technical training, including jar testing at your site, safety presentations, and the installation of safe chemical handling and dosing systems. I am a graduate of Illinois Wesleyan University, Bloomington, Illinois, with a BS degree in chemistry, ACS certified. I am also a member and do many presentations at AWWA conferences and WEF conferences, and is also a member of the American Chemical Society. Our other presenter is Zachary Stevenson. I'll let him introduce himself.
Hello, everyone. As Darren said, Zachary Stevenson. I've been with Carus for about a year now, so kind of a newbie. And as Darren said, I'll be, doing everything that he does and hoping to absorb all that information that he has. But prior to Carus, I was at Iowa State University, and I got a PhD in microbiology with an emphasis in geochemistry. And then I've also worked at a biotech company doing different genetic testing and whatnot. So it's kind of an interesting side of my career.
Thanks, Zach. So we'll get started here. So thank you for all attending today's webinar, and thank you for participating. Like I said, if you have questions, enter them in the panel, and if we have time at the end, we'll answer them. If not, we will get back to you after the webinar. So what we're going to cover, presentation topics, and this is a brief Permanganate 101. So it's going to cover a wide range of products, not a ton of detail on all of them. We'll have some case studies throughout, but we're going to cover the different permanganate products that you'll come across in the field. We'll talk a little bit about oxidation and permanganate chemistry. We'll cover a lot of the different oxidation application categories. We'll talk about municipal drinking water. We'll talk about wastewater. We'll talk about industrial applications. We'll talk a little bit about remediation applications, and that will cover permanganate uses and some case studies for those. So permanganate products are available in a wide range, and hopefully you're familiar with our products, but if you're not, this will give you a good brief overview of the products that we sell. Probably our main product and our bread and butter for over the 100 years that Carus has been in business is going to be crystalline or dry solid potassium permanganate. Our brand name is Carus potassium permanganate. Its chemical formula is KMNO4. Potassium permanganate, always going to be manufactured and packaged as a dry crystalline material to use. Occasionally you'll find solutions of this in the field. One of the places you might is that Hach will sell it as a solution for you to use to calibrate chlorine residuals because it's stable and you can use it with the powder pillows to get a perfect reading for your calibration. There are many different grades of potassium permanganate that are available, and they're used in different industries and different applications. Potassium permanganate is very stable. It can be manufactured, packaged, and delivered to the customer site. Typically, we recommend that you use it within 2 years of getting it, but if the product is stored in a cool, dry area in closed containers, it will maintain its strength indefinitely, which means basically forever. We have product retains that we keep in our quality control lab that are 20 years old, and they're going to be the same 98, 97% pure that they were the day they were made. So the grades that you'll see there in the industry, by far the most common is the second, the free-flowing grade, 97% purity. The reason for a little bit less purity in this grade is there is a free flow additive added to the product to prevent lumping and clumping, because permanganate will pick up moisture from the atmosphere and start to clump. So the free flow additive helps prevent that. If you don't need the free flow additive, you can go with technical grade. It still has a very tiny trace amount of free flow additive, but you can see the purity goes up 1% because we have a little less of the free flow grade. And then specifically, if you have an industrial application that requires certain metal content, we have a pharma grade and an ACS reagent grade. We also have a remediation grade. They'll all be 99% pure or higher. And depending on the grade, there'll be different metals testing or other testing that we do that we certify for those products. Product is packaged and sealed in containers from as small as a 5-gallon pail of 55 pounds, 330-pound drums. We have cycle bins, and we also have bulk for the dry product. One other product that you might not be familiar with, even if you are familiar with permanganate, is Carus potassium permanganate nuggets. This product is basically clumps of dry permanganate. You can see in the picture there that they vary in size from kind of large pebbles to kind of smaller pebbles. This product is about 94% active as permanganate, and it's used for lagoons, lift stations, where you basically want something that's a little chunky that you can throw down. It's going to dissolve pretty readily in wastewater or in a lagoon. It'll dissolve pretty readily as it sinks, but it's used for kind of specialty, kind of small applications like that. Now, one of the big things with potassium permanganate, and the reason why we don't typically sell a liquid solution at Carus, is the solubility of potassium permanganate at room temperature. So you can see a graph here at room temperature. Potassium permanganate is about 5 to 6% soluble at room temperature. Above that, what you're going to end up with is you're going to end up with crystals in the bottom of your tank, and those obviously can plug feed lines. They can plug the feed pump. They're actually pretty abrasive. As you look at the pictures of the permanganate there, it kind of looks like purple sand, and that's how I would describe it too. So it's gritty, it can chew up stuff. So what you really want to do is make sure if you're pumping it, you want to make sure it's into solution. So typically what we tell customers is you want a 3% solution, which is about a 1/4 pound of dry potassium permanganate per gallon of water. With about 15 to 30 minutes of mixing, that will go into solution, and you'll have a dark purple solution that you can then feed through your metering pump. You do want to make sure that you have materials that are compatible with permanganate, and that is information that you can get from us. But you really don't want to be feeding any of the crystalline material through a metering pump because it's so abrasive it will chew that pump up. Now you may ask, why do we have a liquid permanganate if we have potassium dry permanganate? Well, because of the low solubility of potassium permanganate, we have a liquid product, but it's based on sodium permanganate. That product is available as both a 20% active ingredient and a 40% active ingredient. So Carusol liquid permanganate is 20%, and Carusol C, which stands for concentrate, is 40% active ingredient. Potassium permanganate, sodium permanganate do all the same chemistry. It's just the solubility that's the big difference. We sell this product in sealed containers from as small as a 5-gallon jerry can to a 55-gallon drum to totes that are 275 gallons and all the way up to bulk tankers. It's going to look dark purple like you see in the white capped picture there. And then as you dilute it down, it'll look more purple like potassium permanganate solution. So why the difference between the two products? It's really just that potassium versus sodium that changes the aqueous solubility of the product. So what you can see is the solubility for sodium permanganate is much higher at room temperature. We're up in the 40 to 50% range, which is what allows us to sell it at a 20% and a 40% concentration. Now, as you increase to 40%, the product becomes a little more reactive for the containers. So it does eliminate some of the containers that you can have the product in at your site, some of the pump materials that you want to use. But we have plenty of customers that use both 20 or 40% for their application as a replacement for the potassium permanganate. What it really does is it minimizes your equipment. With dry, you're going to have dry product to make into solution. So you might have a feed system and then a tank and then your metering pumps. With liquid, you can feed directly from the container or from the bulk tank with a metering pump directly to your application point. So what is permanganate? So potassium permanganate, like I said, is KMnO4. Sodium permanganate's chemical formula is NaMnO4. And the really only difference between those two products is the solubility. They're both going to be purple in solution. Permanganate is a stable chemical oxidant produced and delivered either as the dry or as the liquid. Because it is stable, it can be packaged, stored, and delivered to the end user. If it's stored in a clear, closed container, like I said, shelf life, we typically recommend you chain product over 2 years, but like product can be good 5 years, 10 years, 20 years down the road. Because it is stable, it is inherently safe to have around. One of the things that we have customers ask all the time is it going to lose strength over time? So if you think of other chemicals that you might be familiar with, like hydrogen peroxide or sodium hypochlorite bleach, those are going to lose concentration over time the longer you store them. With both liquid and dry permanganate, those are going to stay the same 97, 98, or 20 and 40% concentration today, 6 months from now, 4 years from now, 10 years from now, they're going to keep the same concentration. So you're not losing strength if you're storing the product, which is a great benefit if you're using something where you don't need to use it on a regular basis, like you may only use it in the spring and the summer and the fall and don't need to use it in the winter for odor control. Or in drinking water, you're using it for disinfection byproducts and you only use it in the summer months. You can store that product over the winter months and use that product in the spring, and you're not losing any benefit from that product. It's going to be the same concentration. Now, one thing that customers sometimes jokingly say is a drawback for permanganate is going to tell you where it's at in your system. Permanganate is distinctly pink to purple based on concentration. So what you see here in the picture is from as low as 0.5 all the way up to 100 milligrams per liter. Also could be referred to as parts per million. And permanganate, whether it's potassium or sodium permanganate, is going to have that distinctive color. As permanganate reacts, that pink to purple color is going to go away, and you're going to be left with manganese dioxide solids, so particles that you're then going to have to filter out a solution after you've done the treatment. But once you've applied permanganate to your wastewater or your drinking water, you're going to be able to tell where the permanganate is if there's active permanganate, because you'll be able to see that color and you can actually measure it with different test methods. So where does permanganate fall as far as chemistry? It kind of naturally fits into two chemical categories. It is a manganese compound, and manganese is a transition element that is like iron, found throughout the environment. It's present in soil, water, plants, and animals that we live with every day. So it's throughout our environment. Permanganate is also an oxidizing agent. This is the product that Carus manufactures and uses in the field, and our customers use in the field to oxidize things. One of the easiest ways to think about what an oxidizer is, or an oxidizing agent, is an oxidant is packaged energized oxygen. And we'll talk about this here in a little more detail. So one of the easiest ways to think about oxidation, you can have this result from kind of things you come in contact with in your physical world. So we live in an atmosphere that includes oxygen that we breathe on a daily basis. It was noted that almost all elements form some type of oxidized compound just through exposure to the air. When heat and light are involved, this rapid oxidation is typically referred to as combustion. So the easy one we think of, you've got metal that's exposed. It oxidizes in exposure to the elements. And in the case of like the iron in a car or steel, you can see that it rusts, it's oxidizing. In the case of combustion, you can think of lighting a match or starting a fire. You're getting both heat and light during that oxidation reaction. To a chemist, it's more accurate to consider oxidation as a transfer of electrons from one element to another. Now, this means that oxidation reactions are always going to be paired with a reduction reaction at the same time. You can't have one without the other. So as a chemist, what we would talk about, the oxidizing agent or oxidant is responsible for oxidizing another substance and itself ends up being reduced. Electron loss, oxidation, is reflected in an increase in the oxidation number. So what you're going to see is you're going to have an oxidation agent and a reduction agent that are going to go in these reaction pairs. And then we'll refer to something as the oxidizing agent and something as a reducing agent. And we'll show that in these next couple slides with some equations. So in the case of iron, you've got iron that will be soluble in solution, which is that first iron molecule that you see there. And then you have potassium permanganate in this case, but it would be the same for sodium permanganate. That's going to be oxidized from soluble, which would be ferrous iron. When it oxidizes, it's going to turn to ferric, and it's going to precipitate out as ferric hydroxide. The permanganate's also going to go from soluble manganese, which will be the pink-purple color. It's going to be reduced to manganese dioxide. So we're going to get a precipitate of manganese dioxide out of solution. So you can see both of those things dropping out. In this case, one of the rules of thumbs that most people in drinking water or wastewater know is that if you have one part of soluble iron, so ferrous iron in water, it's going to require roughly 1 part of potassium permanganate in order to oxidize it. In the case of sodium permanganate, because of that change in molecular weight, it's a little less, so it's 1 part of soluble iron requires 0.84 parts of sodium permanganate. So just rules of thumb that you can use. If you know you've got iron and manganese you need to oxidize in your drinking water or your wastewater application, you can kind of walk through the chemistry of how much permanganate you would need. In the case of drinking water, our goal is always to get below that SMCL that you see at the bottom, which is a secondary maximum contaminant level of 0.3 for iron. Iron is very easy to oxidize, whether it's permanganate, air oxidation through aeration, chlorine dioxide, they're all going to oxidize iron to help remove it. Some of the other things that we might, if it's an organic material, the chemistry might look something like this. So you've got an organic molecule in the C6H5OH plus permanganate, and you're going to generate manganese dioxide again, and then you're going to break down that molecule and split it in part. So one of the things you'll note in this reaction is, depending on the thing that you're reacting with, on the organic side, some of the reactions will go all the way completely to carbon dioxide and water. Sometimes they'll go to partial oxidation. So you can see here that we're breaking down and we're creating 2 smaller organic molecules, whereas sometimes you want to go all the way to CO2 water. So it's going to really depend on what you have in your water, what the organic compound is, and how much permanganate, how much time do we have, do we get partial or do we get full oxidation. One of the things that's important in the case of something like phenol, partial oxidation is all we need. We need to get rid of the toxicity. You need no more phenol compounds. So if you end up with 2 different partial organics, you're going to still meet your permit for phenol destruction because you have destroyed that compound. Now, this is not a comprehensive list, but permanganate can react with a wide range of different types of organics. It really depends on where we're starting. And then there's many different compounds or reactions that are possible. Things that we typically react with: alkenes, alkynes, alkyl side chains, alcohols, organic sulfur compounds, organic nitrogen compounds. So if you have a question about a specific compound, please feel free to reach out to us. We can look up the chemistry and see if it will react, and then also have an idea of how long does it take, what kind of compounds do we get from that breakdown. So that's one of the things we like to do as technical service at Carus, is help you. If there's things that you don't know, we can help you with some of that chemistry. Now, one thing to keep in mind also, and we'll ask you a little bit, besides just the compound, we're going to ask you about some of the reaction conditions as well. So oxidation reactions typically are impacted by the pH. So typically it's the extremes. Most of the time permanganate reactions are done between pH 6 and 9. So we're right in the neutral, slightly acidic, slightly basic. If we start to go at the extremes, lower than pH 5, higher than pH 12, there are some different reactions that will happen that will affect the chemistry. So above pH 12, you're starting to get to a point where you could actually decompose permanganate just because of the strong caustic concentration. So if you take caustic soda and blend it with permanganate and you get too high on the pH scale above 12, the permanganate is going to go from the purple color to green, and you'll lose an electron and it will be manganate. So you'll definitely see that color change. It'll go from purple to green. And what's happening is that concentration of alkaline content is actually losing a little bit of your reaction chemistry at that point. Sometimes we do have caustic permanganate solutions, but we try to a lot of times stay in that 10 to 12 range and not get too high so we don't lose some of our oxidation power. At lower pHs, you can get permanganate acid, have other side reactions. The other issue is that lower pHs, typically you don't always get the manganese dioxide to precipitate out a solution, or some of the metals that you might have in solution to precipitate out as well if you need metals removal. So generally what we would do is suggest moving the pH up to the 5-6 range so that you can get precipitation of the manganese dioxide and those other metals that you're trying to remove. So we've talked a little bit about the different types of products, a little bit about the chemistry. So working with oxidants is important and valuable because they're pretty versatile. So let's start with some very simple chemistry. Oxidants can be used to do a couple different things. They can synthesize new chemical products involving a very specific reaction condition and procedure. Example for this would be the manufacturing of saccharin. It's made with a permanganate oxidation. Oxidants are also very effective at breaking down unwanted pollutants and impurities. An example would be with the removal of phenol from a wastewater application to make it less toxic to the environment. With this, I'm going to hand it off for Zach for some of our permanganate categories.
Awesome, thank you. So we're going to get into the uses of commercial, oxidizing agents such as permanganate, and these can be broadly placed into one of four primary buckets, which include the synthesis, purification, or cleaning of other chemicals and materials, the bleaching to eliminate color that is within genes when producing products such as paper or textiles that are white. Also controlling pathogenic organisms through disinfection or therapeutics. However, permanganate is not a registered disinfectant, but does have disinfecting properties. And lastly, the environmental uses for breaking down natural and man-made pollutants or impurities. And so the use of permanganate in various environmental applications continues to be the area where we are most active. And so I wanted to provide these different application points to everyone today. And so above, some of the pictures that you see are from air scrubbing, water and wastewater municipalities, refineries, or even in situ chemical oxidation through soil blending or injection. In drinking water, we are removing some sort of contaminant such as arsenic or radium, taste and odor compounds, or kind of the major one that a lot of you may know is iron and manganese control. And whenever we are with a new customer as technical service, we always are trying to look at different injection points for permanganate pending the type of water plant that we are servicing. Specifically for a groundwater treatment plant, we're usually going to be talking about some high hardness water with not much organic content, little TOC, And with permanganate, it'll be injected in the raw water itself coming out of the well, and this will have very little contact time. But usually we're going to inject in the headspace of the filter, as you see above with that little bit of pink purple color. And what we're trying to accomplish is oxidizing the dissolved sulfide or iron manganese coming up that you will then need to filter out as the solids build up. Green sand filters can use permanganate to keep themselves oxidized, which gives you this nice reaction removal. Moreover, you can have a continuous regeneration with a constant permanganate injection. Another method is a filter can be charged with permanganate without the need to continuously apply any to the front end. And so this gives you a capacity, and then you only need to recharge so often. Now, with this method, you will want to flush any excess permanganate and iron and manganese buildup from the system. With surface water treatment plants, we always want to inject as soon as possible. So one way is at the raw water source or the pump station, right at the initial intake structure. But we can also, if your intake structure is close by, you don't have that long distance, we can add it at the rapid mix at the plant. But like I said, it's still about that contact time. We will want to assess it and see where it will be best used for you. And if it's early enough, we can react with the iron, the manganese, organics, and even cyanotoxins. Of note, as it reacts, you do form, as Darren was saying, these manganese dioxide solids, but these do build a nice small flock. And then if you have your coagulation flocculation, you can create the larger flocks prior to sedimentation. Also, you don't want any residual permanganate, as you know, that purple color. If you see that downstream, might cause for alarm. But we do know that it will all be reacted before the sedimentation actually occurs. And you can always contact us. We will help you on where to put it, how much to use, etc. One recently at a plant, they are deciding to add powder activated carbon. And so applying permanganate before powder activated carbon, you will react with some of the permanganate, which could defeat that purpose. So it's having that idea that if you do add a new chemical or a new strategy, that there might be a need to shift dosing on the permanganate. So really going into the specifics of surface and groundwater applications, as you see in the table, with the surface water, it'll be based on the contaminant. So with natural inorganic species, iron, manganese sulfides will be the main contaminants that we're oxidizing. But the other side of the organic matter is your taste and odor compounds, algal toxins, you have color, TOC, DOM, NOM, etc. But on the flip side with groundwater, you have similar to the surface water on the inorganic species, but include radium and arsenic. We see, a lot of radium customers within the Illinois area. However, because it is groundwater, you really are focused on the color or TOC. So this can be a pretty busy slide, but glad Darren went first to kind of discuss the reactions with the inorganic compounds. So the key in understanding this slide is those stoichiometric reaction mechanisms. Manganese will be 2 parts of permanganate to every 1 part of manganese. Iron, as Darren said, is that roughly 1-to-1 ratio, but in both cases, you will form manganese dioxides and iron oxides that will need to be removed through filtration. With arsenic oxidation, you'll go from that +3 to the +5 state, which is still a dissolved form, but it does adsorb to iron and manganese oxides, which can then be filtered out for removal of this. Hydrogen sulfide in particular has roughly a reaction rate that's between 2 and 4 parts of permanganate for every part of sulfide. It will, and this will generate sulfur and sulfur compounds, but if you have that nice odor smell of hydrogen sulfide, this will get rid of that. To look specifically at the oxidation of dissolved manganese, this is a very common reaction for permanganate for the oxidation and precipitation of dissolved manganese 2+. So we want to really hone in on that 2+ state. You can see that there are two reactions paired together. In one permanganate, the MnO4 is reduced from a +7 oxidation state to a +4, which is the manganese dioxide, or MnO2, by accepting electrons. The dissolved manganese on the left-hand side, that +2, is oxidized and changes from the +2 oxidation state to a +4 manganese dioxide. This unique reaction is known globally in the water treatment industry, and it provides a very practical function for for many municipalities and even new people that are still trying to learn why people might use permanganate. Getting into the radium removal, now this is a common application, especially in Illinois area, as I said. There is no oxidation of radium itself, but radium sticks itself to hydrous manganese oxides for removal, and you make a 1% solution using permanganate plus manganese sulfate, which will make a slurry of manganese dioxides. As you see in the photo, it's kind of that brown solution there. And a lot of municipalities will make this at their plant, and they target a roughly 1 milligram per liter as manganese, and you can get roughly an 80% removal rate. Kind of looking back at the organic functional groups, permanganate, as Darren alluded to, is reacting with alkenes for the basis of the bio test for unsaturation in organic compounds. This test involves the decoloration of a permanganate solution. Carbon-carbon triple bonds in particular are usually oxidized to form diketo or other cleaved products. However, little is known about alkane oxidation by aqueous permanganate under neutral conditions due to low mutual solubility. Alkyl groups attached to aromatic rings are oxidized more readily than the ring itself in most cases, but complete oxidation to carboxylic acid does usually occur. Primary and secondary alcohols, these are rapidly oxidized. These can form your carboxylic acids and ketones. Moreover, permanganate oxidation of organic sulfur compounds is utilized in drug manufacturing and odor control applications, as we'll see soon. And then the oxidation of amines produces hydrozones, aldehydes, and ketones. But one thing to keep in mind is with the amines, you can make ammonia sometimes. Odor characteristics are, everyone, if you're working in wastewater, odor compounds, you'll notice these chemicals instantly. And so they'll have very distinct shapes and elemental structures. On the basic side or on paper, these molecules always will look flat, but we know they're three-dimensional. We can all smell them. And so in this figure above, we're highlighting some of the functional groups based on arrows of the molecules, such as aromatic phenolic groups, alcohols, and unsaturated double bonds. These are important when we go out to investigate how permanganate could help solve an odor problem, because these are specific areas where permanganate will attack and oxidize that odor compound to get rid of the issue. Getting into cyanobacteria, this is one area becoming more of an issue for systems as we've seen increases in algal blooms on lakes, rivers, even streams, and this can cause clogging of intake structures, which would then increase coagulant demand. This means you would need shorter filter runs and increases in filter backwashes. Also, you might need to increase your chlorine demand, which also would increase the potential for disinfection byproduct formation. And a major drawback for the cyanobacteria blooms, as some of you may know, is that some of these organisms can produce cyanotoxins, which can then get into the system. And then also within the distribution system as a whole, you can have an increased chance of microbial growth. Looking at specific cyanobacteria and maybe their taste or odors, these can, where large blooms or even moderate blooms can happen, there's different tastes and odors, such as with Anabaena, that first row, this in moderate quantities can have a grassy, musky smell, but in large quantities, you'll flip to this rotten septic smell. Another example at the bottom there, close to the bottom, is Oscillatoria. This in moderate quantities, also that grassy smell, but then if you have a large quantity, it can also switch to a musty or like a spicy smell.
Now, depending the specific organism or cyanobacteria, you can have different cyanotoxins based on the structure. So with cyclic peptides, this is from microcystis or anabiana. They create microcystins as the cyanotoxin, which hits the target organ of the liver. Now, some can make structures of alkaloids, polyketides, and amino acids, which can all form different cyanotoxins from various organisms, such as the cylindrospermopsin, saxitoxin, or even anatoxin, to name a few. And so these are all things that you might be looking for if you have a plant that has known algal bloom. When we look at permanganate oxidation of cyanotoxins, and as each year passes and we're seeing more blooms on rivers and lakes, you can get these cyanotoxins in finished water. And so you might have a discussion on what treatment, what chemical to choose. And so with permanganate, as you see in the table, you can remove microcystin and anatoxin. However, we're not good with the cylindrospermopsin or saxitoxin. And then looking one down with chlorine, it's good with 3, but is not very good at removing anatoxin. And so as you look through the rest of these chemicals, there is not a one-fits-all solution. But you can also do physical adsorption to remove toxins, but these are less likely than oxidizing compounds to remove them unless you're looking at the membranes there for both the extracellular and intracellular cyanotoxins. And so a lot of water treatment plants, they'll do a combination style where permanganate will be fed at the front and chlorine will be fed at the back. They can also add powder activated carbon or even have their coagulation flocculation, which with these combinations will remove all taste and odor compounds, and then also in turn remove the toxins so it's safe for individuals to drink. One case study that is a little bit on the older side but is still pertinent today is we were looking at how permanganate oxidizes microcystin. And so as you look, or as the algal bloom flourishes, you're seeing this increasing concentration throughout the summer, which is that orange line of the microcystin concentration. And then we added permanganate at 1.3 milligrams per liter before the pre-treatment basin, which will then react. And then as we are looking at the finished water, the yellow line on the graph, it is consistently went below the WHO guidelines for the microcystin levels of 0.095 micrograms per liter. Flipping to wastewater treatment, mainly odor control, we can add permanganate into collection systems at the manhole or lift station. These can be added in the clarifiers or even aeration basins, and even added at the back of the plant at the belt press, where you can get some secondary benefits that you'll see here once we get more into this discussion. And this is the one that in our research work, we've looked at very specific compounds that are recognized as odorous. This is one that most people know of, are the list of reduced sulfur compounds. And it's one group of chemicals that are recognized as responsible for a spectrum of unpleasant odors. This group includes hydrogen sulfide, as you see with rotten eggs, or even the allyl mercaptan, which is a strong garlic coffee odor. And one thing in particular, hydrogen sulfide is a common product of anaerobic biological activity. So you'll notice within all the odor descriptions that they're linked to their specific molecules. And there's nothing pleasant about any of these characteristics. But what's interesting is that our noses detect and recognize these chemicals at very low concentrations, as you see for the parts per million on the far right of the table. And this is why the human nose today is still a form in the form of a panel of people. It's used as the analytical tool for odor monitoring and control. But our research work with these odor compounds confirms permanganate's reactivity with the reduced sulfur compounds that you may have in your system. So you might ask the question, when are these odors being released? And so odor compounds that are produced in wastewater plants can be at various locations within the collection or even treatment process. Some of these can be included when air is mixed in, and so that could be open channels or tanks. Maybe during pumping, mixing, or squeezing, or the turbulence, you'll start to get that release of odor as well. And so permanganate is applied to the mostly to treatment processes where it can destroy odor compounds before they are released by that turbulent wastewater flow or wherever that violent stuff mixing may happen. And so what are some of these application points in particular? Well, we can look at collection systems or even the pump station, which are forced or gravity flow pipelines, and they all commonly generate and release odors and are perfect for a permanganate injection. For one plant, pump station, Carus liquid permanganate or even Tolox, which is nitrate permanganate blend, can be fed with a metering pump. As you see in the middle slide, there's a little metering pump on the top. And it's mounted directly on the IVC or drum, and you deliver a measured or timed amount of permanganate dose. Now, because metering pumps are not particularly weatherproof, it may be necessary to mount the pump in a covered box out of the sun and rain. And then in some cases, a small shed may be placed and built at the pump station to house the chemical metering pump and the product to keep it both out of sight and out of the weather, because some people may, if you're near a neighborhood, they could see a chemical and they might get worried. So sometimes people will build a shed just to keep it out of sight. Another application point are manhole areas. These are situations where you may add Carus nuggets or the Carus liquid permanganate, because they're both particularly effective, but they're also good at spot treating. Spot treating with nuggets, they're usually placed, they can be placed in a bag or just dispersed into the system where the water is flowing. And then, as Darren says, it'll dissolve, and then that will be carried throughout the distribution system. Similar to the application point before, the liquid permanganate can be injected, water will flow through the distribution system for the reaction. In the case of treatment plant sites, most of the available permanganate products can be used that we have. Potassium permanganate can be stored and dosed using a dry chemical helix type feeder or mixed as a dilute stock solution and then fed with the chemical metering pump. Notice that the permanganate, when stored and metered as a dry chemical, is always immediately mixed in water, and the water solution is delivered by the pipeline to the injection point. With liquid permanganate, it can be supplied in drums, IVCs, or in bulk deliveries, and just supplied with your simple metering pump that you like. Carus liquid permanganate can be added as a concentrated product. As Darren said, you can always deliver it like that, or you can dilute it a little more using a water transfer line going to the injection point. Carus nuggets, these can be broadcasted into the primary clarifiers where they slowly settle, and that'll treat the accumulated solids at the bottom, and as they are falling to the bottom, they're going to be treating the entire primary clarifier. And then you would decant the water on the top. Tolox may not be effective at a plant site because retention times are too short, and the addition of nitrate plant would increase the nitrogen loading. So that is one caveat there. My favorite one I've been working on, especially this year, but is in biosolids dewatering. So dry solid potassium permanganate and concentrated permanganate liquids are both used in biosolids dewatering applications. With the drying beds can be sprayed with a permanganate solution to eliminate odor emissions while the biosolids are wet. And before they dry, they create this like crusty top layer, as you see in that middle photo. Dewatering systems such as centrifuges and belt filter presses, they benefit the most from permanganate treatment. Dewatering equipment, there's little time for complete chemical reactions with most chemicals, but permanganate reacts quickly, it's very effective. And so there's also these additional benefits as I alluded to before. Not only is permanganate giving that odor control, it also improves the efficiency of common polymers, and dewatered cake often has higher solids content. So permanganate treatment eliminates filtrate odors in the dewatering area and at the process headworks where it is recycled to the treatment plant. After treatment with permanganate, there are no sulfides left over to adversely impact the treatment process by reacting with the needed dissolved oxygen content. So looking at one of our belt press case studies, the main problem within the system or the customer, they had biosolids that went septic, resulting in this high hydrogen sulfide emission. And so they were above the press at about 90 to 100 parts per million. And then within the room, you have around 5 to 8 parts per million. And what's interesting, sometimes when you go into different places with high hydrogen sulfide, if you look up to where some of the metal is, you can see the corrosive nature of hydrogen sulfide. And so after permanganate addition, the belt press levels went to 2 parts per million. And then the hydrogen sulfide in the room was reduced to 0 parts per million. And so not only did we get that odor control to improve worker safety, the polymer usage went from 75 pounds a day to 33 pounds a day, which saved the plant 20,000 annually. In industrial wastewater treatment, this can vary pending the water itself, if it's an industrial wastewater as well. And so we'll look at a few avenues that Carus has worked in. In lagoons, ponds, however you might have it, there's also open clarifiers or even treatment tanks. These are often treated with Carusol liquid permanganate or the Carus nuggets. And these can have an initial one-time treatment where liquid permanganate has been fed by gravity or with a pump, and then even a sprayer. And all these can be from an IBC along the edges of the lagoon. And after the treatment, in one particular instance, we fed the permanganate. After we got what was needed to be done, we were able to then go back and feed upstream of the lagoon to the influent channel, so that you would never concentrating the particular contaminants of concern ever again. And so then you could constantly be treating it and to get rid of that. Now with Carus nuggets, these can be broadcasted just along the shoreline. For a clarifier setup, walk the catwalk, and just above the unit, you can toss them out. And these are really easy in outdoor situations where it may be windy. They're less dusty than Carus potassium permanganate. Even in the lagoon, like I said, you'll get that slow sink through the water column and they're dissolving as they fall, so you're going to get that constant treatment. And many nuggets will reach the bottom of the lagoon where they can treat the odorous anaerobic solids. Now, what's funny, I think, when I first started Carus, interesting, is you can dispense permanganate from a boat, which is quite common. So you'll just see that in that middle picture, a purple-pink trail behind the boat. And so you can always do that with a side-mounted dissolver and just drag it with burlap bags of permanganate through the water. And for landfills with leachate collection, storage, or even transfer, rainwater can pass through open cells of a landfill, which will pick up the odor-causing compounds. And then that leachate is collected into a storage tank and then discharged to a wastewater treatment system. But with the collection of the odor compounds, such as mercaptans, you may not be able to do this. And so individuals will want to treat the tank with permanganate prior to discharge to a municipality or hauled off by a truck to a different facility. Within industrial mining or even hydrometallurgical applications, mainly strip mining or coal mining, this is a big application point due to acid mine drainage. Rainwater collects and picks up iron and manganese in the ponds where this will need to be treated prior to discharge. And so on the right, you can see the addition of permanganate through gravity, as you see that kind of that brown purplish color flowing. And so we can typically get below 1 part per million of iron and manganese in the finished water just after these ponds, which then can be discharged safely to meet any regulatory standards. But pending the processing of certain ores, you may have high concentrations, not only in iron and manganese, but even thallium, which we're going to treat thallium. And these can all be removed by permanganate prior to discharge to a river or stream. Lastly, within agriculture, in the case of this, permanganate has been used in centralized feed operations where there's a lot of odor complaints. Mainly if you've ever gone by a facility, you know that manure smell. And so you can spray on the manure permanganate to help eliminate the odor prior to applying to fields. If it's a liquid manure, you can always treat prior to going into the tanker truck to eliminate the odor and spray. And then you just keep repeating this process for the entire application. And so that's where we rely in the realm of agriculture, mostly the odor control applications. And now I'll turn it back to Darren to finish out on some of the other industrial applications.
Thanks, Zach. So we've covered, a lot of the environmental applications, drinking water, wastewater, some of the industrial applications. So we're going to finish up with a few little different things that you might not know that permanganate's used for. So we'll talk about synthesis, purification, and cleaning. We'll talk a little bit about bleaching, and then we'll talk about environmental, which we really mean is remediation. So permanganate is used as a chemical oxidant in a lot of different synthesis reactions. Like I mentioned earlier in the presentation, one of the big ones is the manufacturing of saccharin. So saccharin oxidation is done from its starting compound to saccharin with permanganate, and it's a very straightforward application. That reaction was done in the US, then it was done overseas in Europe, and now it's typically done in China. A few years ago, when China shut down some of their manufacturing capabilities during the Olympics, they actually moved some of the saccharin manufacture back to Europe. But regardless of where saccharin's made, it's made with permanganate as part of that oxidation process. And it just depends. What kind of compound are you trying to make? There are a lot of different synthesis of organic compounds where you're acting with something. We've worked with companies to make different starch compounds with permanganate reactions. We've worked with other compounds as well to make it. So if you're looking to synthesize something and you think permanganate's a route, feel free to reach out to us and we can explore that reaction with you as well. Purification, besides synthesis, is another thing that we do with permanganate. It's pretty common depending on some of the applications. So permanganate is used in zinc purification. So when they mine zinc ore, one of the things is there'll be other compounds like iron and manganese along in that ore. So as they're purifying the zinc compounds, they will use permanganate to remove those other metals of concern, so they get much purer zinc compound at the end. A lot of that is done in the States, in Mexico, South America, where they purify zinc for that process. You also will see permanganate in the purification of phosphate rock. So one of the steps when they make phosphoric acid, when they mine the ore, they'll end up with a black acid that has a lot of organic content. They will treat it with permanganate, and they can get to both a green stage, so where they'll call it green phosphoric acid. So the permanganate will oxidize some of those impurities, organics and metals, and you'll end up with a green phosphoric acid. And then they can do further treatment to get a clear or a white phosphoric acid. They use other compounds and other oxidizers in this process too as well when they do phosphoric acid purification, but it's just one of the applications. And then permanganate can be used in the purification of acetic acid or CO2. So it's used in a lot of these little specialty applications for purification. Bleaching with permanganate. So we can be used for purification of starches, where we can bleach the compounds out so you get a much whiter starch. The one that everybody's probably most familiar with would be the bleaching of denim. So you can see there in the picture, pretty distressed blue jeans there in both cases. So what they're going to do with blue jeans is they'll treat with permanganate. Permanganate's going to attack both the denim dye, the blue color, and it actually attacks the denim itself, so those fibers as well. Depending on how high the concentration and how long the permanganate's in contact, it will react, and you can see where it's distressing the jean and it's also bleaching the color out. Now there's always an extra step with bleaching in the case of denim. You're going to be left with brown manganese dioxide stains on the blue jeans after you've done this oxidation step. And so then they'll do a reducing agent like sodium bisulfite, which will rinse the manganese dioxide out as soluble manganese. And then you're left with the bleaching effect that you see there, where you've got the white color because you bleached all the color away. And then if you had an excessive permanganate concentration, you can see it distresses the jeans. Always one of the things here, anybody that's worked with permanganate has gotten it on cotton t-shirts or their denim jeans. They don't look fancy like you see there in the picture. You get it in one spot and it puts a hole in your jean just like hydrogen peroxide or bleach would, but it's one of the applications where they're doing it on purpose to make the jean look a certain way. Now, other things that we might bleach beeswax. There are certain clays that we will oxidize to get them much brighter white. and you say, well, you're generating manganese dioxide. Well, as part of that step, we oxidize the compounds that will cause the discoloration, and then we generate a solid, and you can filter that solid out, and then the byproduct that's left behind is going to be the much more brilliant white color. And we can even do that with some biological things like natural sponges. You can see there's kind of a brown color, but they can treat the sponge. You'll get that brown color. You then use a reducing agent, and you get a much whiter, bright white sponge afterwards. So using a lot of different little specialty applications. Metal surface treatment. So permanganate can be used in wire metal plating applications. So part of a chemical cleaning line, a lot of times it'll be a caustic permanganate cleaning line. So they'll have the wire or the nuts and bolts of the other things that they have smut and scale on. They'll treat them in a multi-step bath. So they might have a caustic rinse, they'll have a permanganate rinse, and then they'll have a final rinse. And all that's doing is prepping the surface, removing the smut and scale, so then they can coat that wire or coat that nut or screw with something. So a lot of times they might do this prior to doing a zinc coating. There are other ways to do it, but it is still one of the specialty applications that comes up every now and again here in the US and overseas where they're doing a specialty application. Your cell phone, your laptop, all our little technology with all the tiny little printed circuit boards, permanganate is used in that process. So when they're creating the circuit board with those layers of wafers and the multi-layers to them, one of the parts of the process where they're actually doing high-speed drilling and actually squeezing those things together. When they do the drilling, what they get is they'll get smear back. So when they drill through those layers, the adhesive will come out where the drill happened because of the high speed and the heat. And what they'll want is they will etch and de-smear. So the permanganate solution, along with other compounds, will be used to clean up the smeared adhesive. And then the permanganate, along with those other compounds, can actually etch the circuit board as well to allow them to lay those circuits, transistors, all the pieces that they need. They use a little bit of permanganate along with a lot of other compounds in printed circuit board manufacture. So that laptop, your cell phone, has gone through a process where that circuit board probably came in contact with a small amount of permanganate during its production. Just like wire metal surface cleaning, this would be equipment surface cleaning as well. So permanganate can be used to clean smut and scale off of process equipment. In the case of a refinery, one of the things that you can get is, besides smut and scale, you can get pyrophoric iron that can build up. So permanganate will be used to clean those metal surfaces, detoxify, or even make it safe for you to open the equipment up. So the big one in oil and gas refineries is you've got a lot of compounds that they need to remove before they discharge wastewater, but they also, when they're going to clean or repair a tank, there's some things that they're worried about. So the big one at the top of the list is pyrophoric iron. So pyrophoric iron, when it comes into contact with open atmosphere, will actually get hot, ignite, and start a fire. So obviously a fire in a refinery is not a good thing. So one of the things, if they've got a process tank that they've been storing stuff in for many years, they can have a lot of scale in the pipe that might include pyrophoric iron. So they'll clean the tank with permanganate, and that will remove and reduce the pyrophoric iron so that they can then safely open the tank to do any of the repair work that they need to do. Now, also in that smut and scale in those tanks, there might be phenol compounds they need to remove. There definitely probably will be hydrogen sulfide or mercaptans, odor-causing compounds, so they might have issues with that. They might have iron compounds, they might have cyanide. So depending on what they're processing, are they making oil, are they making gasoline, what products are they making, what type of tank they're treating, they could have a wide range of compounds that they may want to need to treat with that. The picture you see here, this was at a tank where they were storing spent caustic. The spent caustic had hydrogen sulfide and phenol compounds in it. So they had a tote of liquid permanganate set up, the metering pump set up below the tote. And what you see there is we're feeding into the drain line that was going to their wastewater plant. So phenol is destructive to bacteria in a plant. So if they had too high of a phenol level, it would impact the bacteria in their wastewater plant. So in order for them to drain that tank efficiently, because eventually that tank fills and either they have to put another tank on or they have to stop the process until they remove that wastewater. In this case, they were able to treat the wastewater and able to double the treatment flow coming out of the tank, so the tank never got full, with permanganate to remove the phenol on the way to the wastewater plant. So it really depends on the application, but phenol, pyrophoric iron, hydrogen sulfide, mercaptans, all pretty typical in oil and gas. Finish up here, one of the specialty applications would be hazardous remediation. So we do have brand names for this product as well. So Remox S and Remox L, and this would be for Superfund site cleanups. And there'll be a wide variety of ways that they'll inject permanganate. A lot of times in these cases, they're looking at chlorinated solvents. So TCE, PCE, DCE. There can be other compounds as well, like 1,4-dioxane. And there's a couple different ways. So they're trying to clean up a site. Typically, either it's an operating site and they want to clean up the soil and the groundwater underneath the site because it's an operating facility, or the facility wants to sell. And because the site's contaminated and is considered a Superfund, or just because it's contaminated, in order to do that property transaction, they have to clean up the site prior to doing the property transaction. So ways they will do this is they will inject permanganate. So you can see some different injection wells there in the first picture. They might do something if it's bedrock where they'll do a hydraulic slurry emplacement. So they'll fracture the bedrock and then slurry the permanganate in there with a little bit of water. And what that allows for is the fractured bedrock, the groundwater will go through those fractures, but it'll carry through the permanganate slurry and then can carry permanganate downstream. And then one of the easiest ways to do permanganate if it's near the surface is soil blending. So rather than digging and hauling it away and going to a higher class landfill where they'll treat it, you can actually treat the soil on site, mix it with permanganate and water, and then stabilize it with Portland cement. And then leave the soil in place because you've treated it and removed all the contaminants of concern. Just to give you a little idea of how in situ chemical oxidation works with reaction, in this case, the site was characterized. They knew where the plume was. It was underneath a tank that had been leaking into the groundwater and through the soil. And so what they did is they characterized where the plume was, how big it was, and then they built their plan for how many injections they were going to do. So then they injected permanganate through multiple wells, and you can see the rig there where they're drilling the well and they're injecting permanganate. And then as they pull the rig back up, you can see the purple. You get permanganate down into the plume. The permanganate reacts with the contaminant of concern, and basically you can get rid of that source zone of contaminant of concern. So whether it's PCE, DCE, what the contaminant is, you react with it and remove it. And now you've cleaned up the source zone, which means you're no longer going to be bleeding that contaminant off-site anymore after you've done that treatment. So hopefully you learned a little bit about a lot of different applications for permanganate. So we've covered a variety of product forms, grades, packages. So Carus potassium permanganate, the dry form, and Carus liquid permanganate, the sodium permanganate form. Lots of applications: municipal drinking water, municipal wastewater, industrial applications for wastewater, chemical synthesis and purification, bleaching, remediation. So we've covered a wide range of things. One of the things we always like to state is a little bit about safety. So if you're using one of our products or considering using one of our products, you can always reach out to us for the SDS. We have safety presentations, safety webinars that we give. We can come on site if you're a first-time permanganate user and do safety training for you and your staff. But reach out to your regional account manager or your technical solutions, technical service team, myself or Zach. We can get you that information. You can go to our website, contact us, our team. You can find your regional account manager information there as well. What you want to do is make sure if you're using a chemical oxidizer like permanganate that you're storing it properly, you're handling it properly. We want everybody to go home the same way they came into work when they're using a chemical in the field. And with that, there is our contact information for myself, my phone number and email. There is Zach's phone number and email. There is some contact information for Carus as well, and you can always go to our website to find information as well. We're just a little bit over. I'm just going to see if I have any questions, and if we do, see how easy they're going to be to answer in the time we have left. So we have 2 questions that have come in so far, and if you don't get the question asked during the presentation, you can always send us an email. So the first one is, does permanganate have any reduction potential for PFAS compounds in drinking water or wastewater? So unfortunately, no. PFAS compounds are incredibly stable. Permanganate does not react with them, so we don't reduce them. While we've seen permanganate used with PFAS compounds is if there's other compounds like iron and manganese in a drinking water source or at a remediation site, and they're doing something like a pump and treat, they'll use permanganate to remove iron and manganese that would foul the carbon or the anion exchange resin. So they'll have a multi-step process. So they'll take that, at an industrial site, they would take that water for a pump and treat it with permanganate to remove iron and manganese compounds, filter those solids out, and then the water that's much cleaner then goes to the carbon or the anion exchange resin for the finished PFAS removal. And same thing would happen in drinking water compounds. So there are some facilities that are adding that. One up in Minnesota, and they have permanganate pre-treatment for iron and manganese removal from their wells, and then it goes to both carbon and anion exchange basins for treatment after that for removal of the PFAS compounds. How does permanganate remove arsenic? Great question. So we covered a little bit. You probably asked it before we got to that slide. So arsenic is soluble in both the 3+ and 5+ stage. So, but arsenic needs to be oxidized from 3+ to 5+. Once it's in the 5+ state, then it'll absorb onto other compounds in the water. So typically in a groundwater that has arsenic, you'll apply permanganate, and then if you don't have any iron or manganese in the water to react with, you won't be feeding a lot of permanganate, so you'll need to add something to absorb that arsenic that went to 5+. The benefit is a lot of times when there's arsenic in a groundwater source, there's also typically a lot of iron. So you can oxidize the iron with permanganate and you'll get iron solids, and iron solids are very good at absorbing arsenic from the water once it's in the 5+ state. So there's some treatment in some wells up in Wisconsin, Minnesota area where they use permanganate, they have background iron, and they get enough iron so they get arsenic from the 5+ removal in that state. The other way to do it is to add alum or an iron salt to the water after treatment with permanganate. So you get the oxidation to the 5+, and then you add about 1 part of iron or 1 part of alum, and the arsenic 5+ will stick to that, and then that's going to have your flock, and that will settle out. So it's a multi-step process in that case. So at that, thank you guys for attending. If you want a copy of the presentation, please feel free to reach out to either one of us. We can get you a copy of the slides. We will have a recording of the webinar tomorrow that will be available, and we usually do post it to our YouTube page as well, so you can watch it there as well. But we can send you that link to the presentation as well. Thank you for your time.
Thank you.